righty, here we are again in October. Looks like we got about 20 people in here or so, 20, 21, something like that. My name's Julie Kaufman, the president still. And I assume you all got your emails and newsletters, or got them in the mail. And the program tonight is going to be a supermassive black holes. This is Greg Gallagher from Muncie. He's the speaker, and his topic is on super black holes. What are they and what we can learn from them? He's a master student at Ball State University. Also, in the newsletter, I had under my position as eyepiece editor also, Mike Arata, VP, is working on the 2023 speakers coming up, and he's looking for some volunteers to mix in with our other speakers, and it'd be a good opportunity for some of us to reach out and try our hand at being a speaker. You don't have to do anything elaborate, you know, pick your own topic, get with Mike, and maybe he can help you, push you out there. I think I need to do one too, and I'm not much of a speaker. Also, we have 7 new members this month. We had 5 last month, so we're getting hot on picking up some members. Is any of the new members here?
This is my brother Jim, who joined a couple of months ago. Jim Arata.
Okay, Jim. Want to tell us a little bit about yourself, other than your
Well, you might actually hate me because I used to work for that railroad that goes right in front of your observatory. Ground and everything else related to that. But, no, I've always been interested in this kind of stuff, and I have a niece and nephew that are engineers and very much the same. So Mike luckily found me a good deal on a used telescope, and we're just learning to put it together. And my nephew over last Saturday, we got it put together and we found out some more things we need to learn. So anxious to get involved and see what you guys are all about.
That's it.
I just want to say one thing. My wife is at a class in another building and she's unable to walk right now. She suffered a injury, and so I'm going to get text and I'm going to have to go leave at some point. So don't take that as a sign of rejection.
No. we won't. We're pretty easy going.
Okay.
We might rib you about it, but we're okay.
Okay, well, just so you know.
Yeah, yeah.
But, anyway, it's nice to be here. I hopefully get to know everyone this time.
Oh, yeah. There's a lot of good people in here with a lot of different interests. We got spectrometry guys, and there's a few here. And we have people that do photography, people that help you out and learn and just use your telescope. We have some pads outside the observatory where you can bring your telescope as a member, set them up on the pad. We got places to plug in or use batteries or whatever. So yeah, feel free to mingle and find out, different things from everybody. Come out to our Saturday nights and
I shall.
we
shall
return. Anybody have any reports, or I know the weather's been kind of.
Well, I took my a little Max off. It's like a 5-inch, That's the one that took the little picture of Jupiter with,
Yeah.
Yeah, so I had it on a Bogan tripod or something. Just a photographic tripod,
Yeah.
So I took it across the street to look at Jupiter, but my neighbor, I don't think he'd seen that stuff, and he's in the real estate. He looked at that. I don't know if he's gotten out sights on Jupiter, but he liked Jupiter a lot. So that's pretty good, And Saturn, he just thought that was amazing. When people see Saturn, it's like they kind of get it's a jolt in their system. I don't know what it is, but it just.
I remember the first time I saw it.
He goes, "Is that like you can't believe it's like not fake or something?" You know what I'm saying? It just really is kind of cool. So we looked at that, and we looked at. We're able to pick up the Apollo landing site. Yeah, I mean the craters around it. Not the
Yeah, he
actual site.
doesn't. I hope he didn't expect to see the flags or anything.
No, he's smarter than Bradford chair, or real simple. Yeah. So
Yeah, maybe he can come out sometime to the observatory. And show a
well,
lot of
yeah,
basic
maybe.
needs.
If it ever gets warm and I get a chance, I'll take the bigger scope out. His kids and his wife would be interested, but clear night's gotta happen when it's probably not a school night for all that stuff to happen.
Okay. Well, we have a lot of things going on. We have a lot of star parties, a lot of things in the newsletter. And there will be telescope training for if you want to be a key holder and get on the 16 and 12-inch scope inside the meat professional type telescopes. We did have our lunatic party, and Ed, you're flying portrait there and getting into the food. And we had 25 or more people there in line, and we had hot dogs, hamburgers, and then we we all ate and talked, and then we went and did our lunatic thing, looked at the Apollo landing craters and stuff. So it was a great thing. And hopefully we'll do another meet and greet and eat and play, adult playtime.
Yeah, I vote for the Browns again.
Oh, yeah, Laura,
Thank you.
Angie brought the Browns, at least they're not here. Also, John Thomas, who passed away, one of our members, they got some of his books. It'll be at Tech Venture, and there's a bunch of boxes available for review if anybody's interested on Thursday, October 20th. And there's the address in the newsletter. And also, our StarQuest fundraiser is coming up, and that's for the endowment. We're trying to raise $100,000 over time. That we can take money out, and that will support the StarQuest, support the observatory, and the reaching out to the universities and stuff, keep our organization running for the future. And that'll run from November 1st to 20th. We'll have a fund drive, and the money we raise that goes to the community foundation will be matched by 20%. And how much do we got in there now, Phil? Like 30,000, 25,000?
Not that high, it's around 25.
So we're about a quarter there, what we've done last year. And if we raise, we won our category last time. We got a $5,000 check on top of what we raised. So we'll be talking about that. So anyway, is there any other thing to bring up?
Just say, one thing, next month it'd be nice if we had a good turnout. We're gonna have Dr. Watson, Krister Watson from Purdue Fort Wayne Physics Department. He's gonna speak about the Spitzer telescope and Kepler telescope, older scopes apparently that preceded the Hubble scope and so forth. It's gonna be, the talk's gonna be centered on exoplanets. And I think it sounds like it could be pretty interesting. And
Yeah.
I think it'd be nice to have a good turnout for
Yeah, try to drag some of your friends and fellow astronomers and your buddies. You need to get a little more participation. Are you ready, Greg?
Yeah,
So let me
absolutely.
turn out some lights. Somebody want to catch the ones in the back? Is that enough?
Yeah, that's fine. I mean,
Everybody see okay?
Leave the back set alone.
Okay.
We'll fall asleep that way. Perfect.
Okay. All right, you know, Halloween.
alrighty, guys. Well, thank you for having me. I appreciate it a lot. As Jill said, my name is Greg Gallagher. I'm a master's student at Ball State University. Just a little bit about me. Back in 2016, I graduated my undergraduate at Indiana State University. I had kind of 2 degrees in science education and physics, and I wanted to be a teacher. And so for 4 years, I was a high school and middle school teacher in Southern Indiana, Northern Kentucky. And then kind of decided when COVID hit that there was no better time to go back to school. I didn't really want to necessarily deal with that as a teacher anymore. So I decided to go back to school and teach the older kids, right? So I'm at Ball State University now getting my master's degree. And then once I graduate in the spring, I will hopefully move on to a PhD program and pursue a PhD. So my research area is actually in supermassive black holes, specifically blazars, and we'll talk about kind of what the distinction is there in a second. But I really do appreciate you guys having me, and I hope to do a good talk for you guys. So supermassive black holes, what are they? And what can we learn from them are really the two big keys, right? So whenever we think about supermassive black holes, we really think about, you know, what are they, right? Defining them. What do they look like? How do they form? A lot of these kind of big questions, right? But my research specifically is over active black holes, right? Those are called active galactic nuclei. And so we'll kind of talk about that as well, kind of what's the difference, and then kind of go into a little bit of my research there toward the end if I've got some time. Okay. So black holes, okay. I think most of us know that, or at least kind of can guess, right? That black holes are objects that have an incredibly strong gravitational field. They're the strongest gravitational objects in our entire universe. And the kind of idea, right, is that nothing can escape a black hole, and not even light. That's why we call them black, right? And there's this kind of common misconception, though, that black holes are completely dark. And what that kind of means, right, is that they don't emit any radiation, or that they wouldn't emit any light, right? But in reality, black holes actually emit a lot of light. Now, not from the black hole itself, but there's a ton of light that gets emitted from the interactions with the black hole and whatever's around it, right? So it's surrounding material. And so black holes are actually incredibly bright, or at least most black holes are incredibly bright. And you can kind of see this picture that just came out, I think it was maybe a year or two ago. And this is of black hole M87. And you can kind of see what I'm talking about, how bright this is, right? So this is the accretion disk, and we'll talk a little bit about what that is here in a second. That's the accretion disk that's around the black hole. So they are, even though the black hole itself is fairly dark, right? The interactions with the material really lighten up that area, and we can see a lot from it, and we can learn a lot from it. So, you know, I kind of want to cover first how black holes form, right? So typical, what we call stellar mass black holes, are ones that are right around the mass of our sun, okay, form in supernova explosions. And for a supernova explosion, what has to occur is that the core mass has to exceed what's known as the Chandrasekhar limit. All that means, right, is that the core has to be somewhere above about 1.5 times the size of our sun, right? So that's the size of the core of the star, not necessarily the size of the star itself, right? The size of the core has to be above, right around that 1.5 solar masses. And in these supernova explosions, if the mass of the star is above 8 solar masses, so now we're talking the mass of the whole star, right? So if it's above 8 suns, right, the star dies in a very violent supernova explosion, and there's this kind of artist's rendition of what that looks like, right? And so what kind of occurs is, as a star dies, there's these competing forces that are at work, right? There's the force of gravity that's trying to pull everything inward. And then there's also this force pushing outward. That's that pressure. Okay, so there's this pressure from the gas pushing outward, and there's that inner pull of gravity. For most of the star's life, those forces are balanced. So for most of the star's life, they're balanced, they're in perfect, what we call equilibrium, and the star is stable, like our sun, right? Our sun is stable. But as the star starts to exhaust a lot of its nuclear energy in the core, the force of gravity, right, starts to take over. So after it loses kind of all of its pressure pushing outward, right, this gravity pulls inward. Okay. And there's actually something really interesting that happens, because first, as the star is collapsing inward, you have this competing force pushing outward, not from the pressure of the nuclear reactions, but there's what we call the electron degeneracy pressure, okay? And all we really care about there is that we have electrons, which are negatively charged, right? negatively charged electrons don't like to be together. They're like opposite poles of a magnet, right? If you've ever tried to take a magnet, both north poles or both south poles, right, they repel. Same thing is true with charges, right? So as this star starts to collapse, it's forcing these atoms closer and closer together, which forces these electrons closer and closer together. And again, they don't like that. There's that force that repels. There's that Coulomb force is what we call it, and it repels that inward pull of gravity. And if those forces are stable, the result is a white dwarf. If they're not, what happens is the force of gravity continues to push inward, right, and overcomes that force from those electrons being close to one another. And interestingly enough, what it really does is it forces those electrons into the nucleus, and we have a bunch of neutrons. Now, neutrons are neutral particles. They don't have that same force that's pushing out because of the charges, right? So what we now have is this, what's known as the neutron degeneracy pressure. So if the force of gravity is stronger than the electron pressure, we have either a neutron star or a black hole. But now what's happening, right, is you have the physical size of these neutrons. Now they're very, very small, but they have a size, right? And so the force of gravity is trying to push these neutrons closer and closer together. And just like everything else, you don't like to be squeezed, right? There's a limit to how much you can squeeze something, right? Normally. In some cases, if the force of gravity and that neutron pressure, that the force from literally trying to compress the size of those neutrons, if those are in balance, the result is a neutron star, right? So if you've ever heard of like pulsars are typically neutron stars, right? And they're the results of that supernova explosion, but if the force of gravity is equal to that neutron pressure. But what can happen with these massive stars and these massive supernovae, what can happen is the force of gravity can even overcome the size of these neutrons. And when that happens, the force of gravity pushes inward to a singular point. The result is then a black hole. So black holes are formed from the force of gravity being so much stronger. I didn't know that worked. Okay, cool. The force of gravity being so much stronger than the forces that are competing against it, right? So originally you have the force of the pressure from the gas, right, in the nuclear reactions. Then you have the electrons. They don't like to be pushed together, right? Gravity can overcome that. Then we have neutrons, the physical size of the objects, right? And if force of gravity is strong enough to overcome that, we get black holes. And so when we look at a black hole, there are a few things that kind of stand out. First off, we have this disk that's around our black hole. That's called the accretion disk. What happens is sometimes when the black holes get formed from these supernova explosions, there's still a lot of gas and dust and material that's around that black hole, right? There's still the remnants of the star, in essence, that's around that black hole. It can get swept up in the black hole's orbit, and it's moving so fast, okay, that it typically starts to emit radiation, and we see this accretion disk. At the center, that's what we actually call the singularity. That's a point of infinite density. It's where pretty much all of those neutrons, right, that we talked about before and from the core, it's where all of those get compressed to a tiny, tiny point. Around the black hole, we have this last little bright line. I hope you guys can see that. And that's what's known as the photon sphere. And it's just basically the last stable orbit around a black hole where we still get light that can sort of orbit the black hole that doesn't get sucked in, right? The event horizon then is the radius at which nothing can escape. If you're within the event horizon, you're gone. Okay. But there's a difference between sort of these stellar mass black holes, right, or the smaller black holes, and supermassive black holes. Supermassive black holes are black holes that have a mass of about 10 to the 5th. So 10 times 10 times 10 times 10 times 10, right? Or 10 to the 6th solar masses. So 10,000 to 1,000,000 solar masses and above, okay? And they're typically found at the center of galaxies. Our galaxy, the Milky Way galaxy, as many of you probably know, has a supermassive black hole at the center of it called Sagittarius A star, and it is at the center of our galaxy. And the question that we have is really, how do supermassive black holes form, right? We know, or at least we can guess how black holes are formed, right? But these supermassive black holes, the ones that are 10,000, 1,000,000, 1,000,000,000, 1,000,000,000,000 solar masses times the mass of our sun, right? How do those form? There's an interesting little chicken and egg situation here, because like I said, most supermassive black holes are found at the center of galaxies. So the question kind of becomes, okay, did the black hole form first and the galaxy form around it? Maybe from the remnants of whatever caused that supermassive black hole to form, right? Or did the galaxy form first and the supermassive black hole form afterwards? We don't really know. So there's this kind of chicken and egg situation going on. There are some ideas on how supermassive black holes can be formed. So they can be formed if they get enough material, if they eat enough stuff, they can get bigger, right? Like all of us do. And they can become supermassive, right? Some other ideas, right, are black hole mergers, which is kind of what's shown here. There's an artist's depiction of a couple black holes about to merge. So if enough black holes, or if a couple big black holes were to merge together, they could form a supermassive black hole, right? It could have formed from a star collapse or a star cluster collapse. So you, instead of a singular star collapsing, we could have had a cluster of stars collapse. Okay. Or, okay, at the beginning of the universe, we know there were supermassive stars, and it's possible that the supermassive black holes could have formed from the deaths of those stars. So there's a lot of different ideas on how supermassive black holes can form, and we haven't really seen a whole lot of evidence to really support the idea that it's only one mechanism, right? The overwhelming probability is that there's a lot of different mechanisms that could have been at play, and these are just some of the ideas. And so when we look at supermassive black holes, we can classify them as either active or dormant. Okay. Active black holes means that they're actively accreting material. They're actively eating stuff, right? And what's interesting about active black holes is they're actually characterized by a jet of material, and we'll see that here in just a second. But in order for a black hole to be active, it requires two things. First, it requires a relatively strong magnetic field. And then it also requires a very high density of material around the black hole. Okay. And with the black holes and how fast they're moving, that just becomes plasma, right? Those charged particles in essence just become a plasma. Dormant black holes are black holes that are no longer accreting material, so they don't have that jet. Although for some supermassive black holes that are dormant, like Sagittarius A star, there's actually still evidence that they had a jet at one point. So in this picture, we can kind of see what we're talking about with that relativistic jet. Okay. So what really happens is material that's around the black hole in the accretion disk can get caught up in the black hole's magnetic field, because the magnetic field around a black hole is very strong, right? And so relatively strong. And so this material can get swept up in the magnetic field and be jettisoned out and into space. Okay. Those jets are what classify the black hole as active, right? Is if that supermassive black hole has these jets, it's going to be active. It's actively eating material. Okay. Dormant supermassive black holes, like I said, there's still some evidence that they at one point were active. Sagittarius A star, for example, so this is the Milky Way, just looking at it sort of sideways on instead of top down. Right? An interesting discovery was found where if you look at the galaxy sort of above and below this plane, right, the horizontal plane, there's what's known as Fermi bubbles, because the Fermi Large Area Telescope was what discovered these bubbles. Okay. And it's believed that these bubbles are remnants of the jet, because when you have the supermassive black hole jet, there's actually one that goes up, and then there's also one that goes down, right? So it can get swept up this way, or it can get swept down this way. And so you have that those jets pointing in opposite directions. And we see evidence that at one point Sagittarius A star was active. These bubbles that we see in the X-ray and the gamma ray are thought to be the remnants of the jet that would have occurred, or that would have been, or that would have existed when it was active. Now, my research specifically focuses on blazars. Blazars, I know it sounds like a made-up word, I promise. Blazars are a type of active black hole. They're a type of active supermassive black hole. So that means we have these jets of material, one pointing up and one pointing down, right? So they're supermassive black holes, they're active, great. For it to be a blazar, the jet has to be pointing straight at the Earth. And so what we study then out of these blazars is we study what's coming out of the jet. We study the emission from the jets because it's pointing right at the Earth. We're basically staring right down the barrel of the black hole. And so we can get a lot of information about kind of that system. And we'll talk about kind of a little bit more as to what type of information we can get out of them. These blazars, we can further split into different categories. They can be high, intermediate, or low frequency objects. I'll talk a little bit about that here in just a second. Or we can classify them as flat spectrum radio quasars. And the really interesting thing is that blazars typically have two different states. They have states of high activity, which we call the flaring states, and they have states of very low activity, and we call that the quiescent states. Right? So blazars frequently go in between these flaring and quiescent states. They typically go through different periods of activity. Hey, look at that. Cool. So the flares give us additional information about the blazar. Okay. And is one of the reasons why that's the primary purpose of my study is I'm actually looking at a blazar in its flaring state because we can get additional information about what's occurring in the system, right? Because they can be caused by an increase of the density of that plasma, right? So they can be caused by an increase of stuff around the black hole. The black hole's eating more, it's binge eating, right? So it's got to get rid of that, right? And so it could be caused by the increase of plasma density. It could be caused by what are known as kinks in the relativistic jet as well. So that jet can sometimes get, just like a hose, it can get kind of kinks in it. And that mechanism isn't entirely well understood as to why that happens. That's an active area of research currently. One of the ways that that can happen, though, is this magnetic field recombination. So if you've seen like with the solar flares, right, where you have the shearing of material on the solar surface and you get that recombination of the magnetic field, so you get those rings around the sun, okay? That same thing happens in the blazar jets because you've got that plasma, right? So it could be caused by that magnetic field recombination. Now, all active galactic nuclei give off radiation. Okay? And we can see that radiation at different wavelengths in the electromagnetic spectrum. We can see it from radio all the way to what I study, which is the very high energy in gamma rays, right? So they typically give off radiation in a lot of the different wavelengths of the electromagnetic spectrum. For blazars, there's really two different processes that we care about and that we study. There's synchrotron radiation and synchrotron self-Compton scattering. And I'll touch on these just a little bit to just kind of explain why we care about them and what they are. So synchrotron radiation, okay, occurs when you've got a charged particle that's being accelerated around a magnetic field. Okay. There's something that's really, really interesting about sort of the particle physics that's happening here, where you have the particles interacting with the magnetic field. And what's kind of occurring is that when you have the magnetic field, when you have a Coulomb field, so like the electric field, when you have a gravitational field, any field that makes up the fabric of our universe, right? There's constantly energy being pumped in to these systems that then gets released out of these fields, right? So the magnetic field has this energy that's getting pumped in and the energy that's leaving, right? The way that we kind of model this is we model this with what we call virtual photons, where we have energy that gets built up, right? And then energy that gets released. And that energy release, we just kind of model as if it was giving off light, right? So these virtual photons, okay? And when these particles interact with these virtual photons, there's kind of like a collision that happens, right? And in synchrotron radiation, okay, out of that collision of that photon and that particle, okay, you have a collision, they bounce off, right? There's an energy exchange that happens there. And so the photon that leaves, so if you look at this diagram over here, right, the charged particle comes in, the photon comes in, and then again, you just have a charged particle that escapes and a photon that escapes. The light particle, right, the photon that escapes will actually gain energy at the expense of that collision. Okay. So that collision will happen, the charged particle will lose energy and the photon will gain energy. Okay. And that's what we look at with synchrotron radiation, is how much energy that photon has. It's one of the things we care about. Okay.
Greg,
Yes.
I don't think too many people are familiar with the Feynman diagram, so maybe explain that for.
Yeah.
Yeah.
So
Swivel your Feynman camera towards yourself a little bit.
oh, yeah, sorry. So this is what we call a first order Feynman diagram. It's just a little bit of particle physics. It just helps to show these collisions that we're talking about, right? Where these arrows show what's coming into the collision, and then the ones out here show what's coming out of the collision, okay? This middle piece just kind of shows the energy exchange, really, okay? So they're interacting, and then there's that exchange of energy, and they leave. And I really just put this in to kind of show the collision and how we kind of model that collision. So then there's also this synchrotron self-Compton scattering, okay? So we have the synchrotron radiation, right, which is where we get these photons that come out, right? And then these photons can interact with those same particles and pick up even more energy through these collisions. They're just colliding even more with those same particles, right? That's why it's called self-Compton scattering, it's the same population, okay? And so again, the photons are boosted to even higher energies by this process, okay? And it requires a very high density of that plasma, like we talked about, right? So that's why we care about it coming from these blazars, is we have a high enough density of these materials, right? We have enough plasma to have that synchrotron self-Compton scattering. And again, this diagram just shows, okay, we have a charged particle coming in and a photon coming in, they collide, there's that exchange of energy, the particle will lose energy and the photon will pick up that energy. So why do we care? How does this relate to blazars? Well, what we can do is we can model this emission coming from the blazars, okay? So this is the model that we kind of compare what we study to, okay? There are two peaks in the spectrum, right? There's obviously a peak here and a peak here. Okay? These different lines, so the dotted line is for a high frequency object, okay? So a high frequency blazar. This solid line is for a low frequency blazar. The difference is really just where that peak occurs. Okay, so for high frequency blazar, it just shifts the peak. So we get higher energy, we get higher energies basically, right? So this is the energy down here, and then this is like the flux, so how much energy change there is, okay? And so what we do is we model these peaks. Each one of these peaks is dependent or is a different process. So this first peak is from that synchrotron radiation that we talked about. The second peak is from the synchrotron self-Compton. Okay. This is the whole game, is trying to literally build this for every single one of these different objects. It's the whole game is just trying to match with what we see to this and just kind of classifying it based on sort of where that peak happens. Okay, so that's part of my research. My research is really just trying to match these models. Okay. So research on these AGN or these blazars, okay, is conducted really in two different ways. We have space-based telescopes and we have ground-based telescopes. We have atmospheric telescopes, right? So for the high energy and very high energy, so we're talking the gamma rays, right? So if you kind of look over here, we're talking these types, these energies over here, right? Already you can see, oh, hey, we're only going to see one peak for the really high energies, and that's the synchrotron self-Compton. That's kind of what I'm focused on, is really trying to find where that peak is. Okay. But for the high energy and very high energy bands, that entire process actually relies on pair production. Okay. So we're going to chat a little bit more about some radiative processes here. And what happens, and this is kind of interesting, this is happening all around us all of the time in our atmosphere. Okay. These really high energy photons are coming into the atmosphere of the Earth, right? And as we talked about a little bit, there's that framework of the universe, right? We have all of these different fields that kind of make up that framework of our universe, right? And again, there's just that energy buildup and that energy released in every single one of these different fields, okay? And in the atmosphere, we have a lot of different molecules, which means we have a lot of different, protons and electrons, right? So there's that electric field that's made, that each one of these different atmospheric atoms has associated with it, right? And so we have, just like we talked about with synchrotron radiation, how you have a collision, we have the exact same thing happening, okay? We have a collision of an atmospheric atoms field, right? Those virtual photons with one of the real photons coming from our source. There's an exchange of energy, but instead of a collision where they bounce off of one another, in this case, they kind of come together and build up so much energy that the easiest way to release that energy is to actually produce matter. So it's E equals mc squared. That's all it is. Energy gets built up. If with enough energy, you can actually have matter that's created. And this happens all of the time in our atmosphere, all of the time. And in this case, we have an electron and a positron that come out. Okay. And that's sort of how we study our, how we are able to use these ground-based and space-based experiments to study these really high energy objects. The space-based experiments, so like Fermi-LAP, for example, okay, there's some pros and cons to using these different space-based or these different observation techniques, right? So with space-based, it's much easier to conduct, okay? This observation time is essentially 24/7 because you're in space. You don't have to care about when it's dark outside, right? It's always dark. Okay. So it's easier to conduct, okay? However, it's really expensive because you got to fire something into space. That's not cheap. And you typically don't get as big of a range of energies that you can see. So what happens with this, and this actually diagram does a really good job of showing what's happening in the Fermi satellite, but this also could, I mean, you could put the atmosphere in this and it would work similarly. But what happens is that first incident photon, right, that the light that's coming from the blazars, right, collides with one of these foils, and you have that pair production that happens. Same thing that happens in ground-based astronomy. So my research is conducted using the Veritas telescopes, the Veritas array, which is a ground-based array system based out of Arizona. I think Ben's given a couple talks on Veritas here. But the thing with ground-based experiments is that they're not really direct. They're very indirect because we have to rely on the atmosphere. There's an exception of radio, but that's neither here nor there. The observation time is limited because we have to wait for, number one, for it to be dark outside, right? And then number two, there are certain seasons out of the year that we can't do measurements because it's too cloudy, it's too bright. We've got, lightning, whatever. So we don't have the same amount of time that we can use to get these measurements. It is relatively less expensive, and I say that grudgingly. It is relatively less expensive, but you typically do have a higher energy range that you can get to. Okay. And data collection is, like I said, based on pair production, but it's also based on what we call Shrankov radiation. And so when we talk about these telescopes, when we talk about how Veritas telescopes work, okay, it's not the same thing as an optical telescope, right? Where, which I'm sure you all are most familiar with, where you look into an eyepiece and we see these objects, right? Instead, it's digital. It's all camera based. And what happens is you have that pair production that occurs that we talked about, right? And what's really interesting is that when the first electron and positron get created, okay, typically they're traveling faster than the speed of light in air will allow them to. They're traveling too fast, okay? So if you're traveling too fast, you have to give off energy, right? You've got to get back down to a limit that you can be at, right? And the way that these photons do that is they emit light that's in the ultraviolet, so it's just outside of the visible range. I actually had a conversation with my girlfriend the other day because she studies birds, and I was thinking, I know that some birds can see an ultraviolet light, or that most birds can. So I was like, I wonder if they just see a bunch of strobe lights happening all the time. Like, it would be just crazy to be a bird, I think. I would love to know how they see the world for just a day. I just think that'd be insane. Yeah. So anyway, so we have this blue light, and that blue light is actually this ultraviolet light, right? And that ultraviolet light is what we pick up. That's what our telescopes pick up, is that Shrankov light, okay? And it's really just the interactions of how those photons interact with the atmosphere, okay? So we've got those blazars, right? Those blazars are emitting light in a lot of different wavelengths. They're emitting photons, right, in a lot of different wavelengths, okay? Those photons hit the Earth's atmosphere, they generate the pair production, okay? Those pairs traveling too fast, got to give off energy. That energy that they give off is what we see, right? So we can kind of backtrack all of this to how much energy came from the blazar, right? So how much energy that stuff had around the blazar, okay? And so what do we learn, right? Like I said, the entire game is to match models with predictions, or match models with what we see, right? So match kind of what the spectrums that we generate with what we think that it should look like. Okay. So this at the top right, okay, was actually taken from a very recently published paper from 2022. It's one of the Veritas papers that was published, and it goes across the entire electromagnetic spectrum, or at least most of the electromagnetic spectrum. And we see those two peaks, right? It's exactly what we expect to see from our models. Okay. And from where those peaks occur, that kind of tells us more about the system itself. It tells us if, like, it helps us classify the blazar. We can learn more about that jet, because that's where this stuff is coming from, is those relativistic jets, right? It tells us something about the magnetic field strength, and it also tells us a lot about the density of the material that's around the black hole. Okay. Because again, that second peak, right, that synchrotron Self-Compton peak, where that occurs is really interesting to us, okay? Because it tells us a lot about kind of what's happening over time. So my research is specifically over this blazar called S3 1227 plus 25. You don't need to know the specifics of that. But my research is on a flare, okay? So it's where we had a huge burst of energy coming out of this blazar. Right. It was first detected in 2015 on the nights of May 16th and May 18th. The Fermi space-based satellites actually what picked it up first. What's really cool is that when they see something or when any one of these kind of groups sees something, they immediately send out a bulletin to all of these other groups and they say, hey, we see some really cool stuff happening. You should point your telescope to it. And that's what we do. Right. So there's a lot of data sharing that happens. There's a lot of working together and collaboration that happens. And Fermi is the one that saw this flare first, and then Veritas, so the group that I work with, jumped on it and said, hey, okay, let's look at it. And so we have a flare that occurred during the nights of May 16th to May 18th in 2015. And then there's a lot of really cool stuff that happened right after it was announced, and then nobody really took the time to do any of the data analysis. So that's where my research comes in. I'm actually doing the data analysis for it. And so there's not really a known classification. We don't really know where those peaks happen. So we don't know what really is going on in this blazar, right? We don't know really anything about it. Previous publications have listed it as a high frequency object, but my analysis has shown this to be what I call ambitious. So I think that it's not a high frequency. I think it's most likely an intermediate frequency object, and I'll explain kind of why here in a second. And then, yeah, the detection was motivated by communication with the Fermi-lab, so that's why we looked at it. So my research is specifically trying to analyze that flare using the Fermi data and the Veritas data and classify this blazar, okay? And then hope to get one of those multi-wavelength spectrums. So I'm hoping to generate this, but because of my energy range, I'm hoping to be somewhere in like this neighborhood. So starting from here and then going over to the right here, okay? So Fermi kind of picks up this peak right here, and then Veritas sort of picks up this last little piece down here. Okay. So I'm trying to use both of those data collection techniques, both of those different experiments to really see this peak over here. So this is kind of my preliminary results. Really, the only thing to notice is that we don't really have that many data points. We've only got 3 data points right now. And that's because all of the data is really in this energy range. And what we call this is we call it a very soft spectrum because it doesn't have a whole lot of energy. Okay. So that means that that peak that we talked about over here is likely not very high. Okay. Which kind of is what leads me to think that it's an intermediate object and not a high frequency object. Okay. And then this is our sky map. So what we're looking at here is we're actually looking at the data from all of the different nights combined into one, and we're looking at the significance. So what the significance means is it's really how confident are we that what we're seeing is correct, right? And so that middle piece right there, the really bright piece, that's what's coming from the blazar. That's where my telescope is pointing. Hey, great. Look, that's where we have the most significance. So great. I'm very confident that my results are good. Okay. All of these other little objects here, all of these other rings are bright stars. So we have to exclude those bright stars. We don't take those bright stars into account because there's a lot of light that comes through those stars and it can mess with our results, right? We just want to make sure that what we're looking at is our source. And so we draw these regions, we draw these circles and say, hey, don't count anything that's in these circles, right? Because again, it's just kind of how we estimate the background, okay? There was a previously reported result that was in a conference paper that that didn't necessarily totally agree with the results that I'm getting. But that's likely because they just use different, what we call cuts. So that just means that they use different parameters for their research. Typically what that means is that you're letting in more, or you're increasing the amount of total error that you could possibly get into the system. So I haven't really done the analysis again with less stringent parameters, but I'm pretty happy, especially since this is what we're looking at over here, that what I'm getting is correct. So for my research specifically, the next thing is that I'm hoping to generate more than 3 data points. I'm hoping to get more than, or to get more of that spectrum, okay? And then I'll be completing this same analysis, but with the Fermi data and combining them into one section. So that's kind of what I'm doing is, like I said, the whole game is to sort of try to build this guy for this different blazar, so I can see where that peak happens, and then see if I can match it to one of our models. And then I'd like to thank the Department of Energy and the National Science Foundation, and Smithsonian Institute and NSERC in Canada. And then I'd also like to thank the Ball State's Beowulf cluster, which has been very nice and very helpful as well. So with that, I will take questions. Thank you, guys. I know it got kind of technical there at the end with my research. I apologize for that. I just kind of wanted to show sort of how we look at these different objects, right?
So,
Yeah.
You're looking at one particular incidence of one blazar.
Yes.
Yeah. So is that guy gonna repeat or what's happening?
Great question. So it's one of those things that we actually look at pretty regularly. Fermi is one of the best tools that we have for picking up flares, for picking up when that stuff happens, because like I've said before, right, Veritas can't see, or we can't do data collection 24/7. So it's entirely plausible that this blazar will flare again if it hasn't already. It's just whether or not we can pick it up and we can see it in time, because these flares are very short, or they can be very short-lived. Most of the time they're very short-lived. The fact that we see it flaring for 3 nights is actually very interesting, because for this type of blazar, again, those flares may or may not happen. I mean, they can happen within 5 minutes, right? And some can last longer. It just kind of depends on what's happening. Yeah.
Is the amount of material over time changes? Can you get different types of, can you go from a high speed down to a lower speed or change the scale or?
Yeah, I mean, depending on what's
Over a
happening,
long
right.
amount of time.
Right, over a really long period of time, it's possible. Yeah, because I mean, it's possible, right, to go from active to dormant and dormant to active, and it's entirely possible to go from low frequency to intermediate frequency. It just depends on
What it eats?
exactly. Depends on what's really around the system. Yeah.
So I guess that's my question. By analyzing that jet, you know what's actually being drawn into the black hole, what kind of material?
Not exactly what's being drawn into the black hole, other than just kind of what's like just generically, subatomic particles, right? They're just atomic particles, right? So
Space dust mostly,
yeah, I mean, exactly. Yeah, it's
mostly hydrogen.
dust and gas, and
So the spikes are not
it's give me
objects like a neutron star falling in, something like that then gives you the blaze.
yeah, it wouldn't necessarily be a whole neutron star, because what's going to happen is as it gets closer to the black hole, it would start to actually feed off of it like this way, right? So it would start to just kind of sort of feed off of that object from a farther distance, because what's going to typically happen is they'll actually orbit one another. So the black hole would orbit the neutron star, and over time you could have that mass exchange from the neutron star into the black hole. They wouldn't ever really I mean, they could collide at some point, but they would spin for a while before that happened.
So you can't do a spectrum of it. It's probably all soup and big stuff and shredding.
We would see a spectrum, but maybe not necessarily from because it would happen over time, it would happen over a gradual amount of time. So we wouldn't necessarily be able to see a spectrum of just with that, right?
I think you said that to be active, black hole needs a magnetic field.
Mhm.
How does a black hole generate a magnetic field?
Good question. So anytime you have moving charges, you can have a magnetic field, right? And so with these black holes, they're constantly rotating objects, right? And so they have all of that moving charge that's happening. And anytime you have that moving charge, you have these magnetic fields, right? So it's the same way that,
Charges in the accretion disk, though, isn't it?
yes, but then there's also still moving, or the black hole itself is still spinning, right? And still is, it's kind of like how the core of the Earth has the liquid core around the solid core, right? So you can still have magnetized material as well. Yeah.
These two black holes ever interact, or are they so far apart? I mean, does one eat the other one? Or
Yeah. So black hole,
strikes them, or-
yeah. So black hole mergers happen. They do happen sometimes, for sure. And when that happens, they do combine and form like a supermassive black hole.
Well, I have a question and I have two comments. So my question is, how, don't worry. My question is, how much, remind me again, how much exposure time is that?
The exposure time for just the flare?
For the flare, yeah. Like your SkyMap, how much exposure time is that?
So this is going to be right around like 5 hours-ish,
Okay,
5 to 6 hours.
okay. And it's not been detected in a quiescent state, it's only been detected in the flaring state?
Good question.
Yeah.
We've taken data on it in the quiescent state.
Okay.
However, I haven't seen anything yet.
Okay.
So the significance is like less than 1.
Okay, okay.
So it's very, very low. Yeah,
Okay.
it's basically nothing so far. Now, granted, we have about 22 hours of the quiescent state data.
Okay,
I've analyzed about 10 of that, so I've analyzed about half of it, and I'm trying different cuts for it. So I'm doing. I started with medium cuts, and then because that spectrum is so soft, I've gone to soft.
it needs to be soft cuts.
Yeah, it's got to be, if not loose, which I don't even know if loose is gonna.
I
see
think we
anything.
talked.
I
about
expect
it.
to not see anything still. Yeah,
I think we talked to Muncie about like super soft cuts, like this. We'll talk later about that.
that's fine.
I don't want to get.
Well, actually, what's interesting though, really quick,
Yeah.
the loose cuts. So I did this analysis using loose cuts
Uh-huh.
instead of soft. So this is with soft
Okay.
soft cuts. Loose cuts have actually decreased the significance.
Okay.
Yeah.
All right. We'll chat later about that.
Yep.
But
I
but
know. I'm with
My
you.
my comments were, well, I thought it was funny that you showed a VERJ 0521 in one of your slides. Come back.
Yeah.
I think I did the secondary analysis on that one.
Did you really?
Yeah.
Nice.
Yeah.
You use event display, right?
Huh?
You use event display?
Vegas.
Oh, you use Vegas?
Yeah.
Okay.
Used to, I don't use Vegas anymore.
Well, yeah.
Back, yeah.
This paper was just published this year.
No comment.
enough.
But my other comment was about birds and Cherenkov light.
Yes.
And funny story, I learned something about this. Apparently, so Cherenkov flashes are like a few nanoseconds, so I don't think human brain, bird brains would be able to, correct me if I'm wrong here, but bird brains would not be able to process
That's fair.
that. But back in, I think, the 60s, the Apollo astronauts would report seeing flashes of light in their eyes, and it turned out that was Cherenkov radiation. And that was
Was
Cherenkov
it
radiation
from their
from
helmets?
their eyes, the human
The
eye.
human eye?
Instead
Wow.
of, so the medium, instead of being air, like for Veritas,
Yeah.
the medium of the charged particle was actually the human eye.
I think he was human.
Humor, yeah,
Humor inside.
yeah, humor inside, yeah.
That's incredible.
So fun fact.
Yeah, no, fun fact.
Their
I
eyes
like it.
still have the flashes. They were like, okay, we're going crazy.
Yeah.
Wow.
So that still must be going on. right?
That would, yeah,
Oh, yeah,
that would make
no.
me feel like I was going crazy for sure.
Just now there's an explanation for it. But when the Apollo astronauts, they had no idea what's going on because all this stuff was still very much in its infancy too. Like,
Yeah.
Yeah.
Interesting.
So if you were to follow astronaut, you turn your head, you could see what black holes were, is that what you're saying?
If only we're that easy, Jim.
That's true.
Exactly, yeah.
The telescopes that you used, you
Mhm.
mentioned for the, get the other one.
Mhm.
They have like a equivalent to like a camera pixel, so many by so many pixels or?
Yeah, I don't remember how many pixels each camera is, but yeah, so it's, you
For a
know,
Veritas camera?
Yeah.
499.
there you go, 499 pixels.
Oh, that's it.
Yeah.
And it's actually really interesting to see, and I probably should have put a picture of it in the slides, but it's really interesting to see really as you're taking data, see the pixels lighting up, because you can really see when like different flashes happen. You can sort of see when like a car's driving past too, because the pixels will light up brighter, and you get kind of annoyed, but it happens like fairly frequently. This last time when I was taking data, there were actually lightning flashes that were so bright that it killed some of the cameras. Yeah, so then they auto shut off, so they're fine. They didn't like, it didn't break them, but it just turned them off. So we had to stop collecting data that night. And so yeah, they're really sensitive.
Where are those located?
Yeah, so they're at Kit Peak in Arizona, so right outside of Tucson. Yeah, and we have 4. So Veritas is made up of 4 of these gamma ray telescopes. Other questions?
Well, you could always, I don't know how to, you could try to unpin yourself and go to gallery, right click the unpin on the main screen. And put some of it. Anyways, so I think, or maybe it's, yeah, somewhere unpin is up there. Maybe it's under more up there. Hopefully it's not. Yeah, but you're actually, your image is pinned right now, so I was gonna say if you unpin it and select gallery or something.
Oh, remove that. Got you.
But if not, I'll walk up with it.
Oh, got you.
Ask if anyone out there with a question. Oh yeah, looks like we got a little bit of a gallery or something.
Yeah.
I see the Ainsleys and.
Yeah, I'll take any questions. Huh?
We got 1, 2, and one of these. Yeah. Doesn't look like you have any questions, but you know.
Yeah.
Was it Kit Peak that just had a forest fire that they had to fight? Or was that the nearby? One of the
I didn't hear anything about it, so I don't
They lost
think
one
it
of their
was, but-
stacks or something.
I think you're right.
maybe. I haven't heard anything about it, but, and I feel like I probably would have, but I don't know. I may not.
You may or may not know this, when the first slide there showed that black hole with the image a couple of years ago.
Yeah.
I understand this was in the galaxy far, far away kind of thing.
Yep.
Why did they choose something that far away?
Size.
Size.
I mean, yeah, it's really the, I mean, that's, I would assume the reason I would not, I don't know exactly the reason, but I would assume it's the reason, but it looks like good. Yeah.
So the limit on detecting it is the angular resolution to be able to resolve it in the sky. And M87, I forget the mass, but it's enormous, it's a huge black hole. And the angular size on the sky of that black hole is almost exactly the same as Sagittarius A star, which is obviously much closer because it's at the center of our galaxy. So there was actually, I think there were 2 teams working this.
Yeah.
And they were.
Well, they had a
competing which
lot
star
of
to look
different,
at.
yeah.
So they, they were looking at both, they're both about the same angular resolution.
But this one's got a lot less stuff in the way though, right?
Yeah, that's true as
It's the
well.
center of
Yeah.
our galaxy, you've got a lot of.
Yeah.
A lot of dust.
Yeah.
So that's a good question. I mean, if we could see M87, and I don't know how far that is, that's a pretty long distance.
Mhm.
Maybe 1,500.
I don't know.
The redshift is actually kind of small. It's like 0.0085 or something like that.
Yeah, but, okay.
In terms of
so-
redshift, it's small, but.
Right.
So it's brighter, a lot brighter. That's all I'm saying, right? M87. Okay. So what happens is ours gonna wake up someday and like, holy guacamole?
So that's a good question.
Yeah,
Even
see it not,
even Sagittarius A star does still give off radiation. It doesn't, we don't necessarily call it active because it doesn't have the jets, right? But it still does sort of take in some material that's around the center of the galaxy, and it does, we like to say it burps sometimes, so it does release some energy, but it just doesn't, there's not a dense enough, like the material around Sagittarius A star isn't dense enough
Okay.
to actually form those jets and have it be active again. It'll be interesting to see what happens with the evolution of Sagittarius A star and then the supermassive black hole at the center of Andromeda when we eventually collide.
Yes.
No, yeah, thankfully, we will not have to worry about that. Yeah, exactly.
So any thoughts about the chicken and egg issue with black holes and galaxies?
I mean, both kind of have their, I mean, as most things, I think it's probably something in the middle. I think some may have formed first or may have formed and then galaxies formed around it. And then I think some probably formed from the formation of galaxies. One of the things you kind of learn is that there's not really one way things happen. There's a little, yeah, I mean, there's, yeah, right. No, exactly. It's kind of like, yeah, no, it's kind of like the universe just kind of likes to experiment and make some cool stuff sometimes. And so I think it's probably some combination.
So well, the other thing I was gonna ask you about is the lunch for dinner tonight. But can the black hole, can it like, after it eats something, can it like have a bulge or a ring or, kind of like, like, I mean, no, I mean, it's a sphere, but you could have a distortion as something enters the thing. Can it?
So we don't see anything from the event horizon. So once particles actually go, so.
But the black hole can itself be like distorted if a large mass gets into it, or, I mean, can it, like I'm thinking like it's a big bowl of jelly, but maybe my physical picture is pretty messed up, but like it can't oscillate or anything.
Black holes are weird. They've got, so they're singular points, right? So they're not really like, so you don't really have a physical size. Like the thing about black holes and the reason that they have an infinite density is because they don't really have a size to them.
Yeah.
Right. So it's just kind of, it's one of those things. It's like once the material gets inside the event horizon, we don't know what happens to it.
Yeah,
right. So it's possible that there could be something that.
Just picture you got a black hole that's mass 10 suns, right? And then another big, sun comes flying by and it's 10 suns, and as it's merging into it, I mean, at some point they're kind of, I mean, does it end up looking like a peanut? Like,
yeah, I mean,
or does it have a bump on the side, or is it always perfectly spherical or not? That's what I'm saying. Is it?
Yes.
Yes, it's always perfect.
I'm just saying yes to everything. We don't really know exactly what's gonna, like, what necessarily the shape of it. I know. I'm sorry.
Sorry.
Oh, you're good.
You look like peanut for less than a second.
Yeah. Yeah.
When I look at that picture. My brain tries to.
Mhm.
Yeah, but what I'm saying, my brain tries to interpret. The yellow and the orange I see is very.
Mhm.
And that place is something further.
So
Other side, perhaps partially. Eclipse the event horizon.
yeah, so
When you're talking about merging, when you're talking about the event horizon, it's all we're going to see. The event horizon.
right.
So we were talking about, so, well, once something drops below the event horizon, you don't care. And as far as the observer is concerned, the event horizon is the end of it.
Mhm.
Light stops there. Okay. Interpret it, you know. Except
Right.
all the curves are together.
Yeah, once it crosses the event horizon, we have no idea really what's exactly good. I mean, we have models that we can try to figure some stuff out, but really we have no idea.
Jim, you could have possibility of two separate event horizons. And while those objects are merging, you would get your peanut. For
Yeah.
that 1/1,000th of a second.
Right, for the
Line
very
of
brief
relative
period, yeah.
speeds, Right, but once the two holes themselves occupy the same point in space, it would be perfectly circular.
So they don't ever do like, wow.
Well, so this is the crazy thing about black holes and event horizons.
Yeah.
The singularity is here, and there's this huge swath of territory before you get to the event horizon.
Yeah.
And so you could still actually be orbiting
Inside of the
inside
event horizon. Right.
You can't leave, and your orbit's going to be screamingly relativistic fast in terms
Yeah.
of speeds because of the gravitational pull. So you could get two black holes that are
Orbiting.
so
Yeah.
fast. And that's where we sometimes get these gravity wave experiments showing like a
LIGO.
ripple.
Yeah.
Usually we see it with neutron stars, but you can probably see it with black holes spinning into each other.
So like if a supermassive black hole, if they're so big, can you possibly enter one and not get ripped apart? Like you're saying, yeah.
At the edge of the
orbit inside
supermassive
one
one,
of it, or-
Yeah.
the tidal forces at the edge of the supermassive aren't that bad.
Right. The tidal force
Small
from your
ones,
head to your foot is
tidal
basically
force
the
will rip
same.
you apart. At a supermassive one, what was that 1980s movie, The Black Hole or whatever?
Yeah.
You're not going to get ripped apart at a supermassive one. You just fall below that horizon, and
Keep falling.
you can still see the outside world. That light's still coming in, but you can't tell them what you're seeing.
I thought like in the time dilation goes so
Well,
fast
time
that
stops.
You would like not see what you see the end of the universe or something. Kind of thing, or not really. Like as you get closer, it gets more and more dilated.
The closer you get to the gravitational well of the hole, the more it's going to dilate. Yes.
I'll stay on this side.
After how many years? Yeah, something like that. Yeah. Wow.
Okay. I mean, the crazy thing is, and what Ray pointed out, you're not actually seeing the black hole. You're seeing all of the turmoil and debris that's falling into it. But you're not actually seeing the black hole itself.
See it all.
In fairness, Greg, I have a PhD in physics, so that's why.
Hey, you're good. All right, guys. Any other questions?
About a year or so ago, I went to Columbus and Dr. Brian Green, who from the Gallagher talk on black holes. He kind of mentioned something you guys were talking about there where actually time. If it's not a spinning, like I said, I forget what it was, but I highly encourage you guys to look up that talk. I forget the name of it, but this was super interesting. This was also incredibly. It's very, very.
I can next week with several books.
Oh,
Okay.
Scratch, turn, apart, I think I knew
Well, thanks.
it.
Yeah, of course. Thank you.
Gonna have to excuse the packaging. It's one of my wife's many gift bags, but here's a small
Thank you.
token. You could open it up. It's nothing spectacular, a little bunch of Fort Wayne coasters, so.
I like that. That's awesome. Thank
If
you.
If you need more, we're kind of short on that.
Oh,
Normally
no,
we
it's
get you
okay.
6 or 7, but that'll probably be good enough.
This is
for,
perfect. Thank
All
you.
right.
Appreciate you. Yeah, no, thank you guys. I really appreciate it.